I will be putting some problems on the board. You can pause the video in between the problems to take all the time you need to work them, and this will help you familiarize yourself with series circuits and Kirchhoff's voltage law. Okay, here's our first problem. We have a 12-volt battery, a 12-ohm resistor labeled as R1, a 10-ohm resistor labeled as R2, and a 2-ohm resistor labeled as R3. What we want to calculate is the total resistance for the whole circuit, the voltage across R1. Recall that when there is current flowing through a resistor, there will be a voltage difference across that resistor. So our voltage will be higher here and lower here. What is the difference? That will be the voltage across R1. What is the current through R1? What is the voltage across R2? What is the current through R2? And what is the voltage across R3? And what is the current through R3? Go ahead and pause the tape, calculate this, and then come back and we will look at the answers. Okay, let's get started. First of all, what is the total resistance? In a series circuit, the total resistance is the sum of all of your resistors. It's like adding batteries together or stacking buildings on top of each other. Everything just adds up. So we have 12 ohms plus 10 ohms plus 2 ohms. That adds up to 24 ohms. Let's put that in red so we can see it a little better. So our total resistance is 24 ohms. Now we need to calculate the voltage across R1. If you don't know your voltage, you multiply. So we multiply our resistance times our current to get the voltage. Well, we don't know the current yet. How can we calculate the current? Well, we know the total voltage and we know the total resistance. If I have so much voltage and so much resistance, I will have so much current. So if I take my total resistance and divide it into my total voltage, that will give me my current. So let's do that. 24 ohms divided into 12 volts gives us 1/2 of an amp of current. So now I have a current meter showing the amount of current flowing into R1. And that is 1/2 of an amp. I've expressed that in milliamps. A milliamp is 1,000th of an amp, and it's very common to express quantities that are less than 1 amp as a number of milliamps. So 1/2 of an amp, or 0.5 amps, equals 500 1,000ths of an amp, or 500 milliamps. So there's our 500 milliamps flowing into R1. There's our 12 ohms. So we don't know our voltage, so we multiply. So 12 times what? 500? That's 1/2 of an amp. So 12 times 0.5 gives us 6. And here it's shown higher voltage here, lower voltage here, so positive to negative, 6 volts across the 12 ohm resistor. And we've already determined that the current is 500 milliamps. Okay, now we move to R2. And the question is, how much current is flowing through R2? Well, this is a series circuit. There's only one path for the current to flow. And it's like a horse race or a car race. If we have a race with 10 horses in it, no matter where you go around that circuit, you're going to see 10 horses. And they're the same 10 horses. So I go to any turn around the race course and count the horses, I will count 10, and they're the same 10 horses. So if there's 500 milliamps here, it's going to continue and flow through this resistor. So we have 500 milliamps flowing through R2. And so that was a bit of a trick question. Yes, the current is the same everywhere. So no matter where we are in the circuit, we have the same current, 500 milliamps. Might as well put it here. So now the question is, what is the voltage across R2? And once again, if you don't know your voltage, you multiply. We have 500 milliamps times 10 ohms, so that's going to be 5 volts. So there's our 5 volts across R2. Now, this is not an exercise in calculating Ohm's law. We used Ohm's law to calculate these two, but it's equally as important to get the concepts of how these voltages are distributed. So we know the voltage is distributed in the circuit according to Kirchhoff's voltage law, which states that the voltages across the resistors must add up to the battery voltage. So if we have 6 volts here and 5 volts here, that's a total of 11 volts. So how many volts are left? We have 12 volts, 6 plus 5 equals 11. There must be 1 volt left across the 2 ohm resistor. So does that add up? 6 volts plus 5 volts plus 1 volt equals 12 volts. Let's use Ohm's law to confirm that. We have 500 milliamps, or 1/2 of an amp, flowing through the resistor, and we have 2 ohms, so we multiply those together to get the voltage. So 2 times 0.5 equals 1. So there is our 1 volt. So using Ohm's law to confirm it, we see there's 1 volt across this resistor, 5 volts across this resistor, 6 volts across that resistor, and 6 plus 5 plus 1 adds up to 12. Kirchhoff's voltage law is satisfied. Here's our second problem. We have a 45 volt battery, 5 ohms, 25 ohms, and 15 ohms. We want to solve for the total resistance, the total current, and the voltage across each resistor. Go ahead and pause the video and solve the problem. First of all, the total resistance will be the sum of the resistors. So we have 5 plus 25 plus 15. That's going to be 45 ohms. Next is the current. 45 volts is the total voltage, and our total resistance is 45 ohms. So we have, if you know your voltage, you divide into it. So 45 divided by 45 equals 1. So there is 1 amp of current flowing through the circuit. Before we start using Ohm's law to solve these problems, this is not an exercise in Ohm's law. It is an exercise in series circuits and Kirchhoff's voltage law. So we want to focus on the concepts of a series circuit. So let's see if we can solve this without doing any Ohm's law. So we know there will be so much voltage across this resistor, so much across this resistor, and so much across this resistor, and those 3 voltages must add up to 45. So let's see if we can find a shortcut and figure out these voltages. We have 15 ohms here, which is 1/3 of our total resistance. So if it's 1/3 of our total resistance, it'll also have 1/3 of our total voltage. Total voltage is 45. It turns out that 1/3 of 45 is 15. So there's 15 volts across this resistor. Almost too easy. If there's 15 volts here, well, if we have the same proportion, we have 15 ohms to 25 ohms, then we'll have 15 volts to 25 volts. So there'll be 25 volts across this resistor. So likewise, there will be 5 volts across this resistor. So our voltages are 5 volts, 25 volts, and 15 volts. Let's go on to the next problem. Now we have 150 volts, 50 ohms, 25 ohms, and 25 ohms. What is the total resistance? It is 100 ohms. So what is our total current? We take 100 ohms, divide it into 150 volts, and we get 1.5, or 1.5 amps. And we'll put that over here. Now let's see if we have any tricks to figure out these voltages without going into Ohm's law. Well, this is half of our resistance, this is 1/4 of our resistance, and this is equal to that. So what do we know? The voltages across these resistors must add up to 150. Half of that voltage must be across this resistor, 25% must be here, and 25% must be there. So what is 1/2 of 150? This must be 75 volts. So 75 volts there, and between these two we must have the other 75. So let's put that up here for R1. And there must also be 75 volts among these two, and they must be equal. The resistors are equal, so the voltage must be equal, and it must add up to 75. So what is 1/2 of 75? That's 37.5 volts each. So now we have 75 volts, 37.5, 37.5. All of that adds up to 150, and Kirchhoff's voltage law is satisfied. This one's a little different. We have 180 volts. We don't know what the value of R1 is. We have R2, and it has 30 volts across it. We already know the voltage across R2, and R3 is 45 ohms. So this time we want to solve for our total resistance, total current. What is the voltage across R1? What is the value of R1? What is that resistor? And then the voltage across R3. Go ahead and pause the video and solve the problem. Okay, what can we do to figure this out? And once again, we're trying to avoid Ohm's law. Let's see what we can figure out knowing the rules for series circuits and Kirchhoff's voltage law. So we have 30 volts here and 15 ohms. So what are the rules? One, there's going to be 3 voltages and they must add up to 180. Another rule is that the voltage is proportional to the resistance. So I have 15 ohms and 30 volts. Here I have 45 ohms. That is 3 times this resistance. So R3 has 3 times the resistance of R2. Therefore, it must have 3 times the voltage. So if R2 has 30 volts, R3 must have 90 volts. So now between these two resistors, we have 120 volts. And we know that the total voltage must add up to 180. So if we have 120, and the rest must add up to 180, what do we have here? 60 volts. So now 90 volts plus 30 volts plus 60 volts equals 180 volts. Now we can figure out what this resistor is using Ohm's law. But let's not. We can still figure it out just looking at the rules for series circuits. If we have 30 volts across 15 ohms, and we have 60 volts here, if we have double the voltage, we must also have double the resistance. So this must be a 30 ohm resistor. Now we can calculate the total resistance. 45 ohms, 15 ohms, and 30 ohms gives us a total of 90 ohms. What is the total current? We have 90 ohms and 180 volts. So now we use Ohm's law. 90 goes into 180 2 times. So we have 2 amps of current. And we figured out the voltage across R1, which is 60 volts. And the voltage across R3 we figured out was 90 volts. Now we have 48 volts, 4 ohms. Now we don't know R2, but we do know the voltage across it. And R3 is 2 ohms. We want to know what's the total resistance, what's the total current, what's the voltage across R1, what's the value of R2, and what's the voltage across R3. Remember, try to avoid using Ohm's law and use the rules for series circuits to figure out these values. Go ahead and pause the video and solve the problem. Okay, let's see what we know here. We have 24 volts across an unknown resistor, a total of 48 volts here. That is half of our voltage. So if this is half of our voltage, that's going to be half of our total resistance. So what do we have here? We have 4 ohms plus 2 ohms, that's 6 ohms. And that's half of our resistance, so R2 must be 6 ohms. So that's the value of R2. So now we have 6 ohms and 2 ohms, 24 volts and unknown voltage, but this is 1/3 of this resistance. So if it's 1/3 of the resistance, it must have 1/3 of the voltage. So with 24 volts here, we must have 8 volts here. Now we have 2 ohms and 4 ohms with 8 volts across the 2 ohms. So this resistance is twice that resistance, so it must have twice the voltage. So we must have 16 volts across this resistor. So let's see if those voltages add up to 48. 16 plus 24 plus 8 equals 48. So the voltages add up to our battery voltage, Kirchhoff's voltage law is satisfied. What's our total resistance? 4 plus 8 plus 2 is a total resistance of 12 ohms. What is our current? We have 12 ohms and 48 volts. Divide 12 into 48. We get 4 amps. And we determined that the voltage across R1 is 16 volts. Before we move on to the next problem, let's look at the voltages as if we were measuring with our black lead anchored there and measure the voltages with our red lead. If we look here, we will have positive 48 volts, the voltage across the battery. If we go here, we have lost 16 volts. So we start with 48 volts, we lose 16, we have 32 volts left over. Now if we move our voltmeter down to here, we started with 32 volts, we lose 24 volts. So what do we have here? 8 volts left over here, which of course is the voltage across this resistor. And so from here to here, we will lose that 8 volts and have 0 volts once we get around the circuit. Of course, once again, we have not run out of voltage. This is not an absence of voltage. It's just the way we are measuring that this is our zero reference, and we are going around the circuit, and we see the voltage go down closer and closer to 0 as the red lead gets closer and closer to the black lead. This next problem is a little different. We have a 20-volt battery and only 2 resistors this time, R1 and R2, and we want the total resistance, the current, the voltage across R1 and the voltage across R2, and we're going to add another little element here, a test point. And sometimes these are labeled as a TP for test point. We'll do that here. Test point 1, I'm not going to label it here just to reduce the clutter, but we're going to see what the voltage is at that point. When we have test points, we assume that we're measuring the voltage with our black lead anchored at some 0 reference point. We'll make that one the negative side of this battery because that's the only appropriate point in this circuit. So now let's take a look at this problem. Once again, we have a 20-volt battery, 2 5-volt resistors. We want to know the voltage across each of those resistors and the voltage measured here with our reference at the negative side of the battery. So pause the video and then we'll solve the problem together. Okay, so we have a 20-volt battery, 2 equal resistors. The fact that they're 5 ohms is inconsequential except for measuring the current, but we have 2 equal resistors, therefore the voltage will be equal, and those 2 voltages must add up to 20 volts. So what 2 equal voltages will add up to 20 volts? And that's obviously 10 volts. So each of these batteries has 10 volts across it. So 10 volts plus 10 volts adds up to 20 volts. There's Kirchhoff's voltage law. Let's put the voltages here. So the next question is, what is the voltage at this point as compared to the negative side of the battery? Well, if I take my voltmeter, black lead here, red lead here, and if I move my black lead anywhere along this line, that does not change anything. So what I'm doing is measuring the voltage across R2. So the voltage I'll measure at this point will simply be 10 volts. I'm not going to label it because it's getting a little cluttered, but I will put that over here. Of course, the total resistance will be the sum of the 2 resistors, so that will be 10 ohms, and the current will be that 10 ohms divided into 20 volts, or 2 amps. Now let's take a look at this in a slightly different way. What I've done is eliminate the battery and the wires leading to it. This is a very common way to draw circuits to reduce clutter. Instead of having the battery over here, which we just assume is there, as I show by these dashed lines here, But we're going to once again eliminate those to reduce clutter in the circuit. So now I have my 20 volts representing the positive side of my battery, and this symbol here, which represents our zero voltage reference, which is representing the negative side of the battery. So just imagine that there's a battery attached to this stack of resistors. And notice that nothing has changed. I have 20 volts here. I lose 10 volts down to 10 volts here. I lose another 10 volts down to 0 here. It's just a different way of drawing the circuit. And we'll be using the same arrangement in the following problems. With this circuit, we have 100 volts between here and here, so imagine there's a 100 volt battery across the circuit. We have 10 ohms and 40 ohms. So what is the voltage at this point here? We have 1/5 of our resistance and 4/5 of our resistance. So what is 1/5 of 100? 20. So we lose 20 volts going from here to here, so we will read positive 80 volts. And of course, that's the voltage across the 40 ohm resistor. Here's another find the mystery resistor problem. We have 60 volts, 40 volts, and 20 ohms. The question is, what is this resistor? Well, we have 40 volts and 60 volts. Here is 40 volts plus this voltage must add up to 60. So we have 2/3 of our voltage here. We must have 1/3 of our voltage there. Remember, the resistors must be proportional to the voltage. So if we have 40 volts and that's 2/3 of our voltage, we must also have 2/3 of our resistance. So we must have 1/3 of our resistance here. So this resistor must be 1/2 of that resistor. So that is a 10 ohm resistor. That may have gone by a little fast. So let's try this again. We have 90 volts and 30 volts and a 15 ohm resistor. What is that resistor? Well, this is 1/3 of our voltage. That therefore must be 1/3 of our resistance. So this resistor must be twice the value of that resistor. So 1/3 and 2/3, so that must be a 30 ohm resistor. So we have 60 volts and 30 volts, adds up to 90 volts, satisfying Kirchhoff's voltage law. Here we want to find the mystery voltage. So we don't know what this voltage is. We know that resistor and we know that voltage. So what do we have? We know there's 10 volts here and some unknown voltage here, adding up to a total voltage. So if we have 10 volts across 20 ohms, if we double the resistance, we double the voltage. So if we have 10 volts across 20 ohms, how many volts do we have across 40 ohms? That's going to be 20 volts. Double the resistance, we must double our voltage. Now we add those up to find the total voltage. 10 volts plus 20 volts is 30 volts. Here's another one. We have an unknown voltage, 20 volts, 50 ohms, and 25 ohms. So what is the voltage at this point here? Once again, we're measuring from 0 here, and we're basically finding our battery voltage. So if we have 20 volts here and 50 ohms, we have half the resistance, so we must have half the voltage. So we have 20 volts between here and here, half the resistance, must have half the voltage, 10 volts. So once again, 20 plus 10 adds up to a total of 30 volts. And this problem is a slightly different style, but it's still the same type of series circuit. We have a 50 volt battery, a 60 ohm resistor, an unknown resistor across which we know there are 20 volts. So let's go ahead and solve this problem. Pause the video for a moment. And let's see what the solution is. We have 50 volts, 60 ohms, and 20 volts. So we know that this voltage and this voltage must add up to 50. So 20 plus watt equals 50. We know that there will be 30 volts across this resistor. So now we have 30 volts and 20 volts. This voltage is 1.5 times that voltage. Therefore, this resistor must be 1.5 times that resistor. So what resistor would fit here? That would be 40 ohms. So we will transfer that over here. And we also have the voltage across R1, which is 30 volts. And of course, the total resistance now would be 60 ohms plus 40 ohms, which would be 100 ohms. And now we can calculate the current through the circuit, which will be 100 divided into 50, or 0.5 amps. So half an amp is how many milliamps? That would be 500 milliamps. Now we're going to do a few quick drills. These circuits are often called voltage dividers because the voltage is divided among the two resistors, and they're used in circuits quite frequently where we have a higher voltage and we want to derive a lower voltage from that higher voltage. So we have here 100 volts, 20 ohms, and 80 ohms. And what we want to find is what is the voltage at this point. Of course, we are measuring the voltage across the lower resistor because when we see this symbol, we know that that is where our 0 volts is. That is where our black lead is anchored in the circuit. So basically we want to find out what's the voltage across that resistor. So what do we have? We have 100 volts, 20 volts, 80 volts. That's 80% of our resistance. That's 20% of our resistance. So we get 80% of our voltage and 20% of our voltage. So what is 80% of 100 volts? Well, that's 80 volts. So the voltage across this resistor is 80 volts, and that's what we will measure here. The next problem, we still have 100 volts, but we have 20,000 ohms and 80,000 ohms. Remember that the K means times 1,000. So 20,000 ohms and 80,000 ohms. We still have 80% of our resistance and 20% of our resistance. So we still have 80% of our voltage and 20% of our voltage. So the voltage has not changed. It's still going to be 80 volts. The next problem, we have 100 volts, 10K, and 40K. Well, you notice I've simply cut my resistances in half. So I still have 80% of my resistance and 20% of my resistance. So 80% of my voltage, 20% of my voltage, nothing has changed except for the current. And the last problem, we have 100 volts, 40K, and 10K. Well, I've just simply flopped the resistors. So I have 80% of my voltage here and 20% of my voltage here. So what's 20% of 100? That's going to be 20 volts. Here's 4 more quick drills. So look at the voltages and the resistors and find the voltages at the 3 test points. Go ahead and pause the video and solve the problems. Okay, we have 90 volts, 30K, and 60K. Well, 30 plus 60 adds up to 90, so there's 1 volt per 1,000 ohms. So there's going to be 60 volts and 30 volts. So this will be plus 60 volts. Here we still have 90 volts and 15K and 30K, but look, the proportions are still the same. We still have a 2-to-1 ratio between this resistance and that resistance. So we still have a 2-to-1 ratio of voltage. So we're still going to have 60 volts to 30 volts. So it's still going to be 60 volts at this point. Now we have 120 volts, 20K, 80K, and 20K. Well, it doesn't take long to notice that that adds up to 120K. So once again, we have 1 volt per 1,000 ohms. So we start with 20K, 1 volt per 1,000 ohms. That's going to be plus 20 volts. Then we have 80 volts across here. So 20 plus 80 equals plus 100 volts, leaving the other 20 volts across this 20K resistor. Notice there's 20K, 20K, 20 volts, and then 80 volts in the middle. And last but not least, we have here still 120 volts and 10K, 40K, and 10K. Notice the proportions are still the same. I simply cut my resistances in half. So once again, we have 20 volts, and 80 volts. So plus 20 20 plus 100.
If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.